once you work on the one tape Turing machine, then you may have the question that as we are going to, as Turing machine has thought about the human computer, working on one tape, single tape, you may think that the power of the one tape Turing machine may not be as good as the human computer. So people have gone for the variations in order to simulate the human computer, but whatever variations you can go, you will come to know that the power of basic Turing machine, which is one tape Turing machine, is the same as the power of the variations. Once you go for such variations where you can go, instead of using one tape, you can use the multiple tapes, then even also you will find the power of the machine will remain same. Once we say the power of machine here, we are not measuring the efficiency, or we are not measuring the convenience or time. What we mean the power of machine is the language or the problems that you can solve in the basic Turing machine. The same problem you can also solve in the variations of this Turing machine. Or you can say that whatever problem you can solve in the Turing machine, where you can have the more number of tapes instead of only single tape, then the same problems you can also solve with the help of one tape Turing machine. That's why power of the Turing machine is remains same. So here we are not adding the convenience or speed. So simply the meaning of power is the problem you can solve in multi-tape Turing machine, the same problem you can also solve in the one tape Turing machine, or whatever variations you can go. So you will see that we are going to see some few variations of the Turing machine. Then you will come to know what are the possible variations. So one minor variations is what? So here actually we have used one tape Turing machine. In basic Turing machine, we generally have used one tape, and this one tape is squared off. We have divided into the square, and in every square we are writing one symbol at it. Okay, so and this is the left-handed tape. So in our basic model of the Turing machine, we have seen one single tape which is the left-handed, and we are writing the symbols, every one symbol in every square of the tape. When there is nothing, we mean that there is a blank symbol. So this is the basic model where we have used only one tape. So whenever you you use the one tape, what we have done, you can write the symbol on the tape, like you can write the symbol like 0 in the square where head is scanning, you can write, and the same times from this position you can move the tape head to the right side, or you can move the tape head to the left side, or you can go for the left side, or you can keep the tape head stationary. So writing the symbol on the tape and moving the tape head, these are the two different actions we are going to perform in this case. So in the variations, once you go for the variation, the one minor variation is that, okay, instead of doing this thing, means you are writing on the tape and you are also moving the tape head to the left, right, or you are keeping the stationary. So in one variations, people think that, okay, moving the tape to the left, you can move the tape to the right, but you should not keep the tape head stationary. So you can write the symbol on the tape, then you can move the tape head either to the left, or you can move the tape head to the right, but you are not supposed to keep the tape head stationary. So this is the minor variations. So in this case, what happened means tape head should not be stationary. This means move tape head to the right, or to the left. Okay, but not keep tape head stationary. Okay, you should not keep the tape head stationary. This means the output of the transition function will be from the set. So your transition function will look like this. So your transition function will be like this. You have delta, you are in some state q, you have the tape symbol, or you have the blank. Okay, and then the output of the transition function will be either state from the set q, or you can have a halting state HA or HR. Okay, and you can write something on the tape, or you may have the blank symbol, and the movement of tape is generally permitted to the either left side, or you can move to the right side, but stationary move is not possible. So the transition function will look like this in this variation. So in the first variation, what you have done, what you have seen, that moving, you are writing tape symbol onto the tape, and at the same times you are moving the tape head to the left or to the right. But in this variation, we are not keeping the tape head stationary. So the, how you can this, if you go for these variations, then in our basic model, where we can keep the tape head stationary also, so you will see that if you have the this kind of machine, or if you have the machine basic model, you can obtain the machine of this kind. So it's very trivial, you can say. So if you want to keep the tape head stationary, then what you need, you can just, you need, if you want to keep the tape head stationary, then what you can do, so if you are at the, say, if you are at the state P and you want to go to the state Q, okay, and once you go to the state Q, you are going to change X to the Y, and if in the basic model, if you want to keep the tape head stationary, okay, then how you can simulate this move in this variation. So for simplicity, you can say that P, you are in the state P, you are going to the state Q, and while going from P to Q, you have replaced X to the Y, and actually you should not keep the tape head stationary. You can move the tape head to the left or right, since the tape is left-ended, and if you are not sure whether it is the at the left end, then it is better to go for the right. You can move the tape head to the right. Once you are at the state Q, okay, then whenever you are at the state Q, then you can say that what is your job? Your job is to again place back the tape head to the position where you are going to, you have to scan the symbol Y. So you just say that you can go to the, so instead of going from P to Q, you can take some intermediate state Q dash, and then you can go to the state Q, and once you are at the state Q, then whatever is there, whatever symbol, whatever, once you move the tape head to the right, you may have some tape symbol. So whatever tape symbol is there, say that tape symbol may be some X dash may be the tape symbol, where X dash can be anything. It can be tau, or it can be blank, whatever. So it can be any one symbol from the tape tau, or it can be blank. So you are not changing this. You have the same tape symbol, but you are moving the tape head to the left. So once you move the tape head to the left, actually then you have this situation. So here you have the x, you are going to change this x to the y, and your tape head is scanning the symbol y, you are at the state q. Okay, so your tape head is scanning the symbol y. Here what you have, you are at the state q dash. Once you are at the state q dash, you have what, whenever you are at the state q dash, so you have some tape symbol, say x dash. Your tape, you have some x dash. So what you are going to do, you are not changing this x dash. Without changing this, you just move the tape head to the left, and you have the left. Once you move to the left, then you are having the symbol y. So whenever you are at this position, then you have your tape head is scanning the symbol y. So actually you can understand like this: you are at the p, and you have the, your tape head is scanning the x, and you are changing to the y, and your tape head is moving to the right. So you change to the y, you are moving the tape head to the right. So once you are at the q dash, the right may be the symbol like x dash. So your tape head is scanning the symbol x dash, and from the q dash, once you make this kind of move, x dash replaced with x dash and go to the left. Once you are at the left, so you are at the q, and your tape head is scanning the symbol y. So actually basically you are doing this kind of job. So it may happen that in one machine you may need more transition, you may need more state, but it is possible to do the same job in this variation as in case of the basic model of Turing machine. Okay. So the next variations, in the next variation, we see that you are not allowed to do the two things simultaneously, means writing onto the tape and moving the tape head. Both is not allowed. Either you can write the tape symbol or you can move the tape head. So writing and moving the tape head is not allowed. So either you can write in the second variation or you can move the tape head. So the output of the transition function means writing onto the tape. Okay, writing onto the tape and moving the tape head. Moving the tape head is not allowed simultaneously at the same time. Okay, at the same time. So in this variation, what we are going to do, you can write the symbol or you can move the tape head. So the value of your transition function will be like this. So you have the transition function delta, which takes from the q, and you can have tape symbol or you can have the blank. Okay, and the output of transition function in this variation is any, you are going to the any state, you may have the HA on HR. Okay, and what you have now, instead of triple, you are having the pair. The output is not triple, now output will be pair. One is the state and other one is the action. Either you are writing on the tape or you are moving on the tape. So the value it here will be, you have the tau union blank. Either you can write any tape symbol or you can replace with blank, or the output can be either L or you can have the output of either R. So this is the possible. So your output of the transition function is the pair now. One is the state and other one is any one value from this set. And in this set, if output is L, it means you are not writing on the tape, you are just moving the tape head to the left. If output is R, you are just moving the tape head to the right. But if output is blank, then you are replacing the symbol with blank. Or if it is from any one element of tau, it means that you are replacing with the symbol available in the tau. So writing and moving the tape head both are not done simultaneously. Either you can write or either you can move the tape head. So in these variations also, we will come to know that if you have this variation, from this variation you can obtain the basic whatever problem you can solve with this variation, the same problem you can also solve with the help of your basic Turing machine. Okay, so these are the minor variation. So in these variations you may think that okay, this is not the generalization actually, and even you are going to restrict more as compared with the basic Turing machine. So in order to truly simulate the human computer, you may think that instead of having one dimensional tape, as we have the human computer, in human computer we have possibly so in human computer we have two-dimensional sheet of paper. So you have the papers, pencil and paper, and possibly you have the two-dimensional sheet of paper. Okay, so you have the multiple lines and you can work on this multi-dimension. So for simulating the human computer actually, instead of taking only single tape and which is the left-ended, what you can do, so you have the left-ended tape in the basic Turing machine we have taken. This is the left-ended tape, okay, and these are the square, and this tape is infinite in right side in this direction. So this is just like the one dimension, but in case of the human computer you can work you can work in you can work from top to down or left to right, whatever dimensions you can. So instead of having the one dimensional tape, you need to keep multi-dimensional tape. So in the variations, you can, one variation says that okay, yes, instead of your tape is left-ended, your tape can grow in both directions. So you are not restricted, you are not making the tape head as the left-ended. In one variation you can extend, you can have the infinite in right side also, and you have the infinite in left side also. So this is the variations. Other variations is that instead of just using only one tape in both, which can grow left side infinite or it can go right side infinite. So instead of using this, you can use the multiple tapes of the left-handed tape. So you can have multiple tapes like this. This is one tape. Okay. This is one tape which is the square 0. Then you can, instead of using only one tape, you can have multiple tape. This is, so you are having the multiple tape. So you can have number of tapes like this. So just like you are simulating the human computer and we are supposed to work in more than one dimension. Okay, so you have the multiple tapes. So whenever you have the multiple tapes, you can work on that. So this is actually, whenever you are using the multiple tapes, this is the multi-tape Turing machine. So we are talking about the multi-tape. This is the multi-tape Turing machine. Multi-tape Turing machine. So this is tape 1. You can say this is tape 1. Okay, tape 1, and this is tape 2, this is tape 3, and so on. You can say that this is tape n. So you have the n tapes in this Turing machine, and now once you are having the n tapes, means you have the multiple tapes, then you can define the further, you can decide the rules, like you can have the only single tape head. You may have only single tape head, and that tape head can scan the same number square at one time. So in one variations you may have the single tape. You can keep the tape head only one, even you have the multiple tapes. So if you are just keeping only single tape head, that can point at one time to every square of this position. Once you move the tape head to the right, then it moves in every tape one position right. If you move left, then it will move in every tape one position left. So if you are keeping just only one tape, you can keep just only one tape. So in this case, in every square, simultaneously you have to scan, and moving right means moving in every tape right side, moving left means moving in the every tape left side. So this you can keep only one tape, or instead of taking simply one tape, you can take individual tape head. So you can say every tape every tape has its own tape head. So the tape head, and it has its own tape head. So at one time you tape the tape another tape head can point to this square. This is square 0, this is 1, this is 2, you can say. And it sometimes the tape head of tape 3 can scan the square like this, or sometimes this can is the tape head of tape 2 can scan the square, say 1, and the first tape head can scan the square this, like 0, 1, 2, and 3. So you are free. The tape head, or every tape has its own tape head. So your tape head can move to the different locations of every tape. So in this case, it is possible to keep one tape head movement left, while other tape head movement can be kept to the right, or even you can keep stationary. So every tape head has its own tape head, so the movement of every tape heads can be done independently. And this actually this is the variations. In this variation, in the multi-tape Turing machine, we are going to use this kind of variations, where you have, instead of having one tape, we are having the multiple tapes, more than one tape, and every tape has its own tape head, so that you can move the tape head in every tape independently. So this is the notion of n-tape Turing machine. So this is n-tape Turing machine. This is so in this n-tape Turing machine, what is the difference? Instead of using only one tape, we have in the basic Turing machine, where we have used only one tape, here you are using more than one tape, and every tape has its own tape head. We have seen in case of basic Turing machine, once you start, then your input is stored in the tape. Now you have n tapes, so in which tape should contain the input? So even you are going to use the n tape, the tape 1 is used as the input tape. The tape 1 is input tape. So we have to use the tape 1 as the input tape, means once your computation begin, then your input is stored onto the tape 1. Also, once the computation is over, then whatever be the output will also be stored in the tape 1. So tape 1 is acting as input tape as well as output tape. So this is used for the two different purpose. One is for the input and other is for the output. So once computation over, whatever output is left, you are going to store onto the tape 1. At the beginning, your input is stored at the tape 1 and all other tapes contents are blank. So every tape has, at the beginning, every tape contains the blank symbol. Every tape has the blank symbol. But only at the beginning, your input is stored onto the tape. So tape 1, in tape 1, at the square 0, you have the blank symbol, and starting from 1, square 1, you can keep the input. Once computation is over, then you have to store the output in the tape 1. In the tape, in the square 0, you have the blank symbol, and output will be stored starting from the square 1. And the tapes from 2 to n. These tapes are used as the auxiliary storage during the intermediate computation. So tape 2 to n are used as auxiliary storage during the computation. Okay, so tape 2 to n, we are using these tape just like for doing the intermediate computation and just for the auxiliary storage. So this is the notion. So in this case, you can define, with this respect, you can define the multi-tape Turing machine. So in multi-tape Turing machine, how you can define? A multi-tape Turing machine or an n-tape Turing machine. Once you say multi-tape, means you must have the tape more than one. So in n-tape Turing machine, an n-tape Turing machine is a 5-tuple. So T is equal to Q sigma tau Q0 and transitions. So just like we have the basic Turing machine, we have n-tape Turing machine, which is also 5-tuple. Means in n-tape Turing machine, we have the number of states, we have the input symbol, we have the tape symbol. Your n-tape Turing machine also begin with the initial state, and it has the transition function. Okay, so but transition function of the n-tape Turing machine is defined like this. So you have the n-tape Turing machine, and you are having some state, and your tape may contains the symbol from the tau, or it can have the blank. Now you need to consider n-tape. So you have to see the contents in the n-tapes. So this is the n-fold Cartesian product. So from this, your output can be, you are going to the state, or you can have any halt state, either HA or HR. Okay, you can go to any one of the non-halting state, or you can go to the halt state, HA or HR, and you can modify the contents of the tape. You can tape symbol can be changed. So you can have tau union blank, and since you have the AND tapes, so you have the AND. So in AND tapes you have to modify. Also, since we have the tape heads of every tape, so you can move the tape head either left or right, or you can keep stationary. And this you have to consider for every tapes and tapes. So this is the transition function for the multi-tape Turing machine. So when a multi-tape Turing machine is a 5-tuple q sigma tau q0 delta, where the transition function is defined like this. So what is the difference in the basic Turing machine? You have to consider the AND tapes content. Here also you have to consider the AND tapes movement as well as the content. So this is the N-fold Cartesian product. Okay. So your Turing machine, multi-tape Turing machine starts. So how transition will look like in the multi-tape Turing machine? You can say, if you are at the state P, you are at the state P, where P can be what? P can be any state from the Q, okay? And you may go to the state R. This is R. And R can be any state from the Q or union HA, HR. So R can be in either any halting state, or R can be any non-halting state. So your machine goes from P to R. Now, for what input? So you have to consider the tape symbol. So say for example, you have the A1, your tape head of tape 1 may scan the symbol A1, tape 2, head of the tape 2 may scan the symbol A2, okay, like this. Tape head of tape N may scan the symbol AN. So this is the symbol. So tape head of 1 is scanning the symbol A, tape head of 2 is scanning the symbol A2, and similarly the tape head of N is scanning the symbol AN. Assuming that AN, A1, A2 up to AN, all such belongs to what? All such can be either tau union blank. These symbols are either the tape symbol or they are blank. Now what you are going to do? Now you can replace, you are changing with different tape symbol like A1, A2, or you are changing to the AN, where A1, A2, AN, all such belongs to the either tau or blank symbol. Then you can have the direction of the tape head. So direction, so tape head 1 can move to the direction D1, D2, and so on. You can say that Dn, where Di from I is equal to 1 to n. This belongs to the set L or R stationary. So D1 can be any one element, either left, right, or S. D2 can be anyone, either left, either left, right, or S. Similarly, Dn can have this. So this is the way you can show in the transition diagram. So you are going from the P to the state, say for example, this is the state R. And once you are going from P to the state R, then you have the transition. Your transition looks like this. So this is the way you can show the transition of multi-tape Turing machine. if n is equal to 3, if n is equal to 3, then what you have? If n is equal to 3, then it is very simple. P, and you are going to the state R. You have like this: A1, A2, A3, and these are replaced with A1, A2, A3, and you may have say L, R, R. You may have the output. So this says that the tape head 1 is scanning A1, 2 is scanning A2, tape head 3 is scanning A3, and you are changing. A1 is replaced with uppercase A1, small case A2 is replaced with small uppercase A2, small case A3 is replaced with the uppercase A3. Tape head first is moved to the left side, tape head 2 is moved to the right side, and tape head 3 is also moved to the right side, and it goes to the state R. R can be halt state also. So this is the way you can show in the transitions. Okay. So this is the notion of your multi-tape Turing machine. So in one tape Turing machine, you have seen that in one tape Turing machine, you have the initial configuration. So configuration of and tape Turing machine. So once you go for the configuration of n tape Turing machine, then how you can show? You can show the configuration like this. Your Turing machine is in currently 8 state queue, and the tape head, you can say the contents of the tape 1 can be x1, a1, y1. Contents of tape 2 can be x2, a2, y2. Contents of tape 3 can be x3, x3, a3, y3, and so on. Contents of tape n can be xn, an, and yn. So this is the configuration of n tape Turing machine, where as usual in the tape 1, the first symbol of x1 will be at the square 0. Here also the first symbol of the x2 will be in the square 0 in the second tape. The first symbol of x3 will be in the square 0 in the third tape. First symbol of xn will be in the square 0 of nth tape. And here q is what? Q is current state. And these are the contents of the tape 1, tape 2, tape 3. Current contents of, this is the current contents of tape 1. This is for the tape 1. This is for the tape 2. And this is the contents of tape 3. And this is the contents of tape n. These are the contents, where x1, x2, and xn all can be taken from the tau union blank. Any strings that that consist of the symbol from the tau union blank. So x1, x2, x3, xn all are the strings from the set tau union blank green star. Also you have the y, y1, y2, yn also belongs to the set the strings from the set tau union blank clean stop. A1, A2, A3 and up to AN. All such belongs to either tape symbol or they can be blank. So A1, A2, A3, AN. These can be the blank also, or they can be any tape symbol. So your tape head is scanning the symbol. In another tape, it is scanning the symbol AN. In the third tape, A3. In the tape 2, your tape head is scanning the symbol A2. Tape 1, your tape head is scanning the symbol A1. So starting from this configuration, okay, this is some configuration of your Turing machine at some state. So configuration of your Turing machine can be given like this. Now, your Turing machine may start from the initial configuration. And what is the initial configuration of n-tape Turing machine? It will look like this. So as usual, the tape 1, assuming that the Q0 is the initial state of the n-tape Turing machine, and we know that tape 1 is acting as the input tape. So at the beginning, the input will be stored in the tape 1. And so at the square 0, it is square 0, you have the blank symbol. Okay, you have the blank symbol, and immediately after the blank you have the X input, and this is what? This is the tape 1. This is the contents of the tape 1. Now if you go for the tape 2, then you will have this situation like this. This is tape 2. Tape 2, at the square 0 you have the blank symbol and everything is blank. Tape 3 also having this blank symbol at the square 0. This is at the square 0. Okay, and everything is blank. Similarly, if you go for the nth tape, then at the 0th in the n tape you have the at the square 0 you have the blank symbol and your tape head is scanning the blank symbol. So this is the initial configuration of your n tape Turing machine. So this is initial configuration. Okay, so this is what? This is in the tape 1, and this is, say, tape 2 and 3, and this is in the tape n. So only tape 1 contains the input and other tapes have all blanks. And starting from this configuration, your n-tape Turing machine T can go to the configuration, halting configuration, like it can go to the HA, and again contents of the tape, say you have the tape, this is the tape 1. The tape 1 can have any value, like tape 1 can have the value like you can have you can write the same symbol like x1, a1, y1. Then tape 2 can have x2, a2, y2, and so on. And tape n can have xn, an, yn. and this is the sum. So x1, x1, x2, xn, all these are the from the strings from the tau union blank symbol. Y1, y2, yn, these are also the strings from the tau union blank symbol. A1, A2, A3 up to an, these are the any tape symbol or blank. So here this is the notion is same. Now if output is important, then the contents of, this is the contents, so you have the contents of tape 1 is the output. So the output, if you are interested for the output, then that whatever be the contents of the tape 1, that is the output. So this is the output. If you are interested with the output, then tape 1 is actually containing the output. And tape 2 to tape n, tape 2 to tape n, these value are rough work. So these are some rough contents. We don't, irrespective of this. So we don't mind the contents of the tape 2 to tape n. The only contents of the tape 1 will be the output if you are interested for the output. And the first symbol of the x1 will be at the square 0. So this is the final configuration, you can say. This is the final configuration, like this. Okay. So whenever you are having the multiple tapes, then your Turing machine will start with this configuration. So tape 1 is the input tape, and tape 1 is also the output tape. So this is the notion of your multi-tape Turing machine. So in multi-tape Turing machine, okay, in multi-tape Turing machine, you have this situation like this. You have to consider the every contents of the every tape at the beginning, and at the beginning tape 2 to tape n will have all blank, only tape 1 will contain the input. So even you have gone for this kind of variation, instead of using only one single tape which is the left ended, you have used multiple tapes, and hence this is the n tape Turing machine. So even you are going to use the n tape Turing machine, whatever problem you can solve with the help of n-tape Turing machine, the same problem you can also solve with the help of one-tape Turing machine. So here actually even you are going for this kind of generalization, just this kind of variations of the basic Turing machine, but you are not able to add more power in this case also. So in fact, whatever work you can do, whatever work you can perform with the help of and tape Turing machine, the same work you can also perform, the same problem you can also solve with the help of only single tape Turing machine. So even you are going for the variations, but you are not able to add more power in the Turing machine. So this is actually the theorem. Okay, so this theorem says that if you have the multi-tape Turing machine, if you have the n-tape Turing machine, then there is an one-tape Turing machine. Then there is an one-tape Turing machine, okay, T2, with tau1 is the subset of tau2, satisfying the following condition. The language accepted by the LT1 is the same as the language accepted by the LT2. This means you can say that if you have some input x which is taken from the sigma star, if T1 halts, if T1 is going to halt, then T2 also halts for the same input. So T2 is going to halt if and only if for some input x, T2 is going to halt if and only if T1 is also going to halt. So that's why for any n-tape Turing machine, we are able to obtain one-tape Turing machine. So that if one-tape Turing machine halts for some input, then your n-tape Turing machine will also halt for the same input. So from in this way, you can say that the language accepted by the n-tape Turing machine and the language accepted by the one-tape Turing machine is same. If your Turing machine is going to provide some sort of output, then if your Turing machine 1 means if your n-tape Turing machine, this is the n-tape Turing machine, this is the n-tape Turing machine. So if your n-tape Turing machine starts with this configuration and it halts in this configuration where this is the contents of tape 1 which is the output, then your one tape Turing machine, this is one tape, this is the one tape Turing. So your one tape Turing machine will also start with the initial configuration for the same input and it halts in the configuration HAX1 A1 Y2 means producing the same sort of output, and this is the theorem. And this is the theorem which says that the power of these two machines are remain same. It means even you are going for the variations, even you are going for using the more tape instead of using just one tape, even you are going for using more than one tape, with the intuition that you are simulating the human computer and possibly you may be able to achieve some more power, but actually you can achieve the same thing with the one tape Turing machine. Whatever problems you can solve with the help of multiple tape Turing machine, multi-tape Turing machine or n-tape Turing machine, the same problem can also be solved with the help of one tape Turing machine. The only you may need to take more number of tape symbols or you may need to take more number of moves. But here we are not talking about the convenience or here we are not talking about the speed. Here we are talking about the power. Power means the problem you are solving, the class of problem you are solving in multi-tape Turing machine and tape Turing machine, the same class of problem can also be solved with the help of one tape Turing machine. And hence, the power of both the machines are same. So power of one tape Turing machine, you can say power of one tape Turing machine, TM, is same as power of n tape Turing machine. Okay, so power of one tape Turing machine is the same of n tape Turing machine. So here, even you are going for these variations, you are not able to add more power in the Turing machine. So these are the some variations we have seen where we have gone for very minor variations at the beginning where we allow the tape head to the move either left or right but not keep stationary. In the second variations, we have seen that writing on the tape and movement of head cannot both cannot be performed simultaneously. So if you are writing on the tape, you should not move the tape head. If you are moving the tape head, you should not write on the tape symbol. Next variation, we have seen that for simulating the human computer, you can go for the, instead of using only one dimensional tape, which is the left-handed, you can grow the tape in both the direction infinite, or even you are using the more than one tape. And here, by using the more than one tape, then you have to uh, frame the rule set for the end tapes, whether you are keeping the one tape head for the that can scan the symbols from the every tape, or you just keep the tape head independent, so that every tape had its own tape head and it can scan the symbols independently. So here we are using this variations, where every tape we assume that every tape is left-handed, and we assume that every tape has its own tape head. So if you are working on the AND tape, this kind of AND tape Turing machine, then this is the actually the concept of multiple tape Turing machine, multi-tape Turing machine. So, and finally we have seen the theorem which says that if you have the multi-tape Turing machine, or if you have the n-tape Turing machine, then there is one tape Turing machine with possibly you may have more number of tape symbols, with condition that the language accepted by the one tape Turing machine is same as the language accepted by the n-tape Turing machine, and also the output produced by the one tape Turing machine is the same as the output produced by the multiple tape Turing machine for the same input. So this is the discussion we have seen. So these are the variations you may find in the books. Possibly you may have some more variations, but question is that whatever variations you can go, you are not able to add the power of the power. You are not able to add more power as compared with the basic Turing machine.